Have you ever wondered why hot air rises? I remember being fascinated by hot air balloons. I mean, because you play with balloons as a kid, and does a balloon stay inflated if it's got a big hole in it? No. Does a balloon float if you just put air in it? No. So how does this work? This balloon has a giant hole in the bottom, it's filled with air, and yet it goes up and it can carry people. What's up with that? It's gases. When you heat a gas, it increases in volume if the pressure is the same. The mass of the gas doesn't change, but if the volume is increasing, that means the density decreases. Density is the mass divided by the volume. So if the mass is the same and the volume is larger, now the density is smaller. Something with a small density floats on something with a large density. The density of the hot air in this hot air balloon is less than the density of the cold air around it, and that causes this balloon to float just like a cork would float in water because it's less dense than the water. By adjusting the temperature of this gas, the hot air balloonist can adjust how buoyant the balloon is and cause it to go up or to go down. Now, there's not really any steering on a hot air balloon. You just kind of have to get into different layers of the atmosphere that are going at different speeds. Any questions? So the volume of a gas increases with the temperature of a gas. So here we have a graph of a gas volume and the temperature. And so we've measured the temperature at about 0 degrees Celsius and higher, and we see this really nice straight line. Extrapolating means that we're going to draw a line past where our actual data is. We draw the line past this, and at some point it's going to predict that there is a zero volume. Now, is it actually possible for a gas to have zero volume? No, it isn't. You take a gas and you can compress it and compress it and compress it. Eventually, though, those molecules are going to get touchingly close, and it is going to have a finite volume. But this line predicts that it could go to zero. The temperature at which the volume is predicted to be zero is called absolute zero. Zero volume is one thing. Negative volume, wow, that is like completely out of the question, right? You cannot get to negative volume. So this is called absolute zero, the lowest theoretically possible temperature. It happens to be at minus 273 degrees Celsius. The Kelvin scale is based on absolute zero. So in the Kelvin scale, zero is at absolute zero. So Charles was a French mathematician and physicist who looked at the relationships between volumes and temperatures of gases. And in his studies, he had a constant pressure and a constant amount of gas. And his law, called Charles' law, is that the volume of a gas and its Kelvin temperature are directly proportional. So the volume of a gas is directly proportional to its temperature in kelvins. You have to use kelvins. Or mathematically, we express it this way: V1 over T1 is equal to V2 over T2. So if the temperature of the gas sample, the temperature measured in kelvins, is doubled, then the volume doubles. But you've got to express the temperature in kelvins. Have I mentioned that? The temperature has to be in kelvins. What unit do we use for temperature in gases? Kelvins. Do we ever use Celsius? No. You have to use kelvins. Why? The problem is that the relationship between Kelvin and Celsius is not just a matter of size of degree. The degree sizes are actually the same. The difference is where 0 is. And so we can't just use Celsius, we have to use Kelvin. The equation of a line is y equals mx plus b. So if we have y being the volume and x being the temperature, if we use the Kelvin scale, then our intercept is 0, and that makes the equation much simpler. And so then we get the V1 over T1 equals V2 over T2. That's the relationship we're using, and so we have to have an intercept of 0. Kinetic molecular theory explains this. If we increase the temperature of a gas sample, kinetic molecular theory says that the gas particles are going to move faster, right? So the gas particles moving faster, they're going to bounce against the container more frequently, which would cause the pressure to go up. But we're keeping the pressure the same. We're allowing the container to expand or contract so that the pressure is the same. So you heat up the gas, it's running around, bouncing around, and so the volume has to increase in order for the pressure to remain the same. This is something you could try at home. Take a balloon, blow it up, not completely as far as it'll go, and then stick it in ice water and see what happens to the balloon. It will get noticeably smaller because the temperature has gone down, so the volume of the gas will go down. If you take that balloon and put it into boiling water or very hot water, you increase the temperature of the gas and the balloon will grow in volume. It's almost magic. So we can do problems using Charles' law, and we're going to take the same approach. A sample of a gas has a volume of 2.8 liters at an unknown temperature. When the sample is submerged in ice water at 0 degrees Celsius, its volume decreases to 2.57 liters. What was its initial temperature in kelvins and in Celsius? So again, we're going to make a table. And identify what all these numbers are. We got 1 and 2. First number I come to goes up here, 2.80 liters. What is that? That's a volume. At an unknown temperature. Okay. Next number, 0 degrees Celsius. So I don't know the temperature, I don't know the temperature that goes with that volume. So there's going to be a temperature here. I don't know what that is. But now we're submerging it in ice water. We're changing things. So now these next numbers I want to write on row 2, 0 degrees Celsius. That's a temperature. What unit did I say we have to use? Kelvins. So before you go any further, just convert this to kelvins, okay? So plus 273, so this is 273 Kelvin. That's the temperature, and at that temperature the volume is 2.57 liters. What was the initial temperature? So here we're looking for T1. So we need Charles' law. Can't use Boyle's law because we don't have pressures, we've got temperatures. So we write out Charles' law. V1 over T1 equals V2 over T2. This equation has fractions in it. Beware. Some of you are great with algebra. Many of you have a sort of, you don't like algebra, and algebra doesn't seem to like you. So for most of you, when you see this equation with fractions in it, we want to get rid of the fractions before we start rearranging things. And we do that by cross multiplying. So cross multiplication means that I'm going to multiply the top of one side by the bottom of the other. So I'm going to get V1 T2. And then I'm going to multiply the bottom of the first side by the top of the second side. So that's T1 and V2. So I have a cross here. Whoops, how did I do that? Cross multiply. That way I get rid of the fractions. Otherwise people end up with really weird stuff. Okay, so now what am I solving for? I'm solving for T1. So I'm going to do the same thing I did with Boyle's law. If I want T1 by itself, I'm going to divide by V2. So the V2's cancel out. To keep it equal, I have to do the same thing to both sides. Got to be fair. I'm going to write this down again. So T1 equals V1 times T2 divided by V2. I have my rearranged equation, and I can plug the numbers in. So V1 is 2.80 liters. T2 is 273 Kelvin. And volume 2 is on the bottom, 2.57 liters. The units, liter, cancel, and so I get the temperature under the first set of conditions is 2.8 times 273 divided by 2.57. I should have 3 sig figs in this. Notice that when we add 0, which had 1 sig fig, to 273, now all of a sudden we've got 3 significant figures. That can happen when we're adding. Everything's got 3. 297.43 Kelvin. So that's the initial temperature in kelvins. It also asked me for Celsius. So to get that into Celsius, I'm going to subtract 273. I'm going to get 24.43. And so my two answers, 297 Kelvin, 24 degrees Celsius. The unit on volume here of liters, this problem would work just fine if that was milliliters or gallons or something else, because those can cancel out. The problem with the Kelvin Celsius conversion is it involves adding, and so it cannot cancel out. So if I use the Celsius temperature here instead, what would the initial temperature end up being? If I put in 0 Celsius, 0 times this divided by that is still equal to 0. But the initial temperature wasn't 0. Why would the volume go down if the temperature didn't change? It just doesn't work with Celsius. And that's probably the most common mistake students make, is they use Celsius instead of Kelvin. We use Celsius when we measure temperatures. I've never seen a thermometer that's calibrated in kelvins. So that's why it's giving you the temperature in Celsius. It's asking for the Celsius temperature, but you have to use kelvins when you do the calculation, because it will not come out the same. Another example, gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters and is heated from 36 degrees Celsius to 155 degrees Celsius. What's the final volume of the gas in milliliters? Okay, same strategy, make a table, collect the numbers. First number, 88.2 milliliters. That's the initial volume. So that's the initial volume. It's heated from 36 to 155. So it started at 36 and it ended up at 155. This is the initial volume, so we want to put the initial temperature with it, 36 degrees Celsius. Convert that to Kelvin before you do anything. I could do that in my head, but I just do not trust my head. 309 Kelvin. Next one is another temperature, so that goes in this column also, 155 degrees Celsius. Change it to Kelvin. When I have one blank, that's V2. It's asking what the final volume is, and that's what I've got there. So Charles' law, V1 over T1 equals V2 over T2. Cross multiply to get rid of the pesky fraction. I want to solve for V2, so I'm going to divide by T1 on both sides. V2 is equal to V1 T2 over T1. You need to show your work when you do these problems. I want you to at least label your variables. Okay, write them down. You can use I recommend the table, but if you want to write down V1 equals T2 equals, etc., that's absolutely fine. But label them, write it down. And then you need to write out the equation with the letters. You don't have to show all of this. Some of you can do that part in your head and just come up with this. That's awesome. But I want this to be written down, and then write down how you're putting the numbers in. Because mistakes can be made in each step, and if we write the steps down, then we can see where we made our mistakes. On an exam, this is important because then you can go back and check your work. You don't have to do the problem all over again. You can just look at it and see, did I do it correctly? Here the kelvins cancel out. So we've got 88.2 times 428 divided by 309. All of those have 3 sig figs. So 122.16, 16 milliliters. So the answer is 122 milliliters. With these simple gas laws, you can also ask yourself at the end, does the answer make sense? So what happened here is we heated a gas from a low temperature to a higher temperature. If you heat a balloon, do you expect it to get bigger or smaller? You expect it to get bigger, right? So heating the gas, the volume should be larger. So look at this. Was my final volume larger than the initial volume? Yes. That's a good sign. Does it prove I did everything right? No. But if it's smaller, then you know you did something wrong. You've got two numbers switched, and you made it smaller instead of larger.